All right, so all of you have had me before, so you're somewhat acclimated to my special brand of crazy. But some of you have only had me for an online class over the summer, so this will be your first time dealing with me in person, for better or for worse. Let's talk about some of the policies and all that kind of jazz in the class. So, oops, I forgot to update that. So let's just start from the beginning. You all know who I am. Obviously, you're also aware of where you are and all that kind of stuff. My office is upstairs in room 211. My office hours for this quarter are going to be Wednesday, Friday from 2 to 5, and Tuesday, Thursday from 3:30 to 5 p.m. Those Tuesday and Thursday office hours are going to be part of the Ada Kappa Nu circuits tutoring stuff. So I probably won't actually be in my office. I'll probably be down the hall in Nefkin room 105. I haven't reserved that room yet, just to be clear. That's where it has historically been in the past. As soon as I get the room reserved for the Ada Kappa Nu stuff, I will put a post on Canvas and let you guys know where that tutoring is going to happen and all that kind of jazz. Let's see. My email address is my last name @lawtech.edu. There's my office phone number, although half of you probably have my cell phone number at this point. Whatever. Emergency class disruption policy in the event that a disaster or anything like that happens, we will be on Canvas and Zoom. Sorry for forgetting to update that. Sign up for emergency notifications at that link, ert.lawtech.edu. Course objectives, we are going to take some of the stuff that we learned in Circuits 1, a little bit of the stuff that we learned in Circuits 2. We're kind of going in a different direction this quarter. So in Circuits 3, we're going to learn effectively about the basics of what you will come to refer to as magnetic circuits when you take your later power classes and all of that kind of good stuff. We're going to get into the nitty-gritty on higher order circuits using analysis in both the time domain, which is going to be you guys' just most absolutely hated thing ever, convolution integrals for those of you that haven't had Math 245. Where you're going to learn them here. If you have had Math 245, you're going to have to deal with them again here. When we get out of the time domain, then we're going to start working in the frequency domain, but instead of using our good old J omega bit of frequency domain, we're actually going to use the Laplace transform to analyze higher order circuits. And you'll come to learn that all of the frequency domain circuit analysis that we've been doing is just a special case of using the Laplace transform to analyze circuits. Then we're going to get into higher order filter circuits. So in Circuits 2, we just covered first and second order passive filters. Here in Circuits 3, we're going to cover higher than second order passive filters. We're also going to have active filters involving operational amplifiers. We're going to be looking at Chebyshev and Butterworth filter topologies for getting higher, well, not necessarily higher gain, but a faster roll off so that our frequencies the frequency response of our filters look more like the brick wall ideal filter response that we talked about in Circuits 2. And if I have enough time, we're going to talk about resonant circuits. And then if I have enough time, we're going to get into some network theory concepts. So a lot of stuff going on, all building on what you guys learned in the last few circuits classes. As per usual, the textbook for this class is Engineering Circuit Analysis 10th edition. And as per usual, I don't expect a single one of you to have ever actually purchased or opened that book. You can use that ULABI circuit analysis and design book that I suggested to you guys back in Circuits 1 or Circuits 2. For those of you who aren't familiar with it, just as a quick heads up, if you Google ULABY CAD, go to the first link, and then it's going to redirect you to a different page. I don't know why there's that intermediate page now. This is a free circuit analysis textbook that will cover 85 to 90% of what we're going to be doing in this class. So feel free to download it and all that kind of stuff. I think it's a pretty good book. It doesn't cost you a dime. The authors are literally giving it away to students for free. As per usual, I am recording all of this. I'll have it posted on Canvas and my crappy YouTube channel and all that kind of jazz, so that you can use this as a reference. Disability disclosure. I feel like all of you heard me rant about this before, but if you have the opportunity to get extended time, you should definitely exercise that. Extended time in this class is only going to be used for the in-class portion of your exams. We'll talk about that more in a little bit, but it can definitely be useful. So if you have that, you should exercise your right to get extended time. Let's see, normal class attendance policy. So officially, it's dealing with policy 2206. Unofficially, as per usual, if you want to be here, great. If you don't want to be here, that's your prerogative. I record everything. Honor code stuff, don't cheat, pisses me off. Academic misconduct stuff, don't be disruptive, and also don't cheat again. Both things still piss me off. Let's see. Oh gosh, there's so many mentions of Moodle in this that I need to update. Okay, homeworks. So it's definitely not going to be like 24 homeworks like it was in Circuits 1, and it's not going to be 17 homeworks or whatever it was like it is in Circuits 2. It's probably going to be somewhere closer to 12 or so. I think I only managed to do 8 or 9 last fall, and it was weighted, or it wasn't weighted, but they were more heavily towards the beginning of the quarter, towards the end of the quarter. So I'm going to try to add a few on kind of in the middle and towards the end so that you guys are getting good practice for everything. I get tired and run out of steam about 3 to 4 weeks into the quarter dealing with all this stuff. So anyway, so not as much of an overwhelming amount of homework as you have received from me in your previous classes, but it'll still be enough to keep you on your toes and all that kind of good stuff. Much like in Circuits 2, everything will be covered digitally, or all of your homeworks and stuff like that will be turned in digitally. So I want PDF in standard engineering format. I don't care about discussion or anything like that. I'll probably wind up putting the homework formatting example that I use in Circuits 2 up and available to you all for Circuits 3 as well. Yeah, so pretty much just the standard homework stuff for me. There will be a couple of design projects. For the life of me, I cannot even remember what those entail right now because it's been a year since I taught this class, so I'll sort that out this weekend. Those design projects will be a practical problem that you're going to do some stuff with, and you're going to run some simulations in LT Spice, kind of just like you did in Circuits 2. So nothing real wild or crazy there. The exams, for those of you that took me over the summer and only had take-home tests, we're going to split things up. So roughly 3/4 of your exam grade will be from an in-class portion of the exam, where that's the kind of standard rules of FE approved calculators and all that kind of stuff like you've done in your other classes. And then the remainder of the exam will be take home. So you'll have either 4 days or a week, something like that, to kind of work some harder problems at your leisure. And then those two things, so the take home portion and the in-class portion added together, will be your grade for each individual exam. If you have any questions about that, please feel free to ask. No cell phone policy for the in-class portion of the exam. Homework's 20%, design projects 15%. Each of the 3 exams are 25%, and then the exam that you do the worst on is reduced to 60% of its original value, so 15%, to come out to a grand total of, let me run through the math here, so 35 plus 65, is that 110?
Oh, it's 135.
Oh, I'm just real bad at math today. All right, thank you for that. So 100%. All right, so it doesn't look like I have any real built-in bonus or anything like that. That's okay. I don't think you guys need it. You're smart enough as it is. Standard 10-point grading scale. If there's needs to be any changes on the syllabus, I reserve the right to do so. More stuff about the emergency notification system, COVID-19 policy. If you're sick, don't show up. That's why I record everything and all that kind of stuff. And I'll be really mad if you get me sick. Counseling services, if you just can't put up with me anymore and you need someone other than your classmates to talk about. I'm genuinely not trying to make light of this, but counseling services are available for free to all Louisiana Tech students. You can sign up using this link, or you can just go directly to the Counseling Services office over in Keeney Hall. Since we have some design projects that are going to take some effort on you guys to kind of look things up, I have a specific AI usage policy in this class. So I'm letting you know where you can use ChatGPT and where you can't use things like ChatGPT. So you can use it for brainstorming in your design projects, helping you kind of understand the topics. There should be a pretty darn big asterisk with that because we've all seen videos and stuff online of how bad AI can be, particularly at understanding some technical topics. I had some students use ChatGPT to answer questions on a take-home test in my electronics class last year. And apparently ChatGPT thinks literally exactly opposite of what it's supposed to about how semiconductor devices work. So anyway, guidance on solving problems, but not just having it give you the solution, and then some assistance in writing and grammar and all that kind of stuff. You can't use it to impersonate you, so you can't just have it generate the solution or steal stuff from other people. And then, unless I tell you otherwise, you shouldn't be using it on the exams. If you do choose to use AI for anything, you are expected to cite it using this form right here. All right. I do not currently have a tentative schedule for this class because some things didn't take as long as I expected them to last year. Other things took longer. So I'm in the process of rewriting that and reorganizing when the exams and all that kind of stuff are going to be. I will hopefully be finished with that this weekend, so I will update this document to get rid of all of the references to Moodle and provide you with a tentative course schedule so that you know when you should expect tests, etc. Hopefully before we have class on Monday. That sound good? All right. Does anybody have any questions or anything? Yes. Yeah. Yep. Well, some of you will have lab on 2 to 5 on Friday, roughly 14 of the 50 of you. Others will have their lab on, I think, Monday and Thursday. Yeah, because I feel like this controls lab is Tuesday, Wednesday. So I think you guys are Monday, Thursday, Friday. So let's talk about the labs very briefly. Actually, now I understand why you're asking that question. Sorry. So you're probably asking that question and saying, how the hell does he have office hours on 2 to 5 on Fridays when he's supposedly teaching our lab from 2 to 5 on Fridays? And the answer to that question is I'm not teaching your lab. It's one of my grad students. I am just the instructor on record. I will try to pop in and all that kind of stuff as I'm able to do so. But Jordan will be covering all of the lab related material and all of that kind of jazz. Because my academic director is trying to make sure that I only have 5 to 6 hours of overload every quarter, as opposed to 10 hours of overload like I had a few quarters last year. Anyway, he's just trying to make it to where I don't literally work myself into a heart attack or a stroke. He's a nice guy. Any other questions? Yes.
Are you teaching Monday's lab?
No. So Monday's lab, at the time of you guys' lab, I have senior design. So yeah, you will, those of you that signed up for Monday will not see me that afternoon. I will be busy herding cats that are seniors. Yes, David. All of the labs are located upstairs in the circuits lab here in Ethican Hall. I believe the room number is 218. Does it not have a location associated with it on workday? Okay, I'll get that sorted out. But we have a circuits lab upstairs here in Ethican Hall. If I'm remembering correctly, it's 218. It literally says circuits lab on the door. That's where you're supposed to go. Okay. Yes.
Do we also have Jordan on Monday?
Yes.
Okay.
Yes. Jordan is the only person who's teaching the 229 labs, and then we've got a different graduate student teaching the controls labs. So, yep, you just got Jordan. For what it's worth, Jordan taught the lab with Dr. Amir last year, so he probably knows more about it than I do because I have not taught the electrical engineering 229 lab since I was a graduate student. So that was at least 7 years ago. So, any other questions? Yes.
When will this class and the lab be open to us on campus?
So this class should be open now. I realized as I walked in that I forgot to publish it when I set stuff up earlier. The labs, Jordan is in the process of setting up, so I would imagine sometime this week. Yep. Yes.
Do the labs start like this week or next?
Next week. So your first lab meeting will be the Thursday people on whatever date is next Thursday. Yeah. So it'll go Thursday, Friday, and then the Monday. That's the sequence or whatever, because our quarter is weird and it started on a Thursday. So the Thursday of next week will be the first lab meeting. Any other questions? Oh, no, you're not. you are not.
Okay, one more question.
Yes.
Let's go 1 to 10. How much do you think
I'm not gonna turn that. I've seen so many of you over the summer and all that and the other. Anyway, no, you guys are great. I'm tired and I'm still on a vacation hangover, and by that I mean I want to be at the beach, not here. So anyway, all right, we've got stuff to do, so let's go ahead and get around to doing that. I'm gonna try to be less distracted than I normally am. All right, so our first several classes are going to be on what I'm going to call magnetically coupled circuits. And we are going to start with a pretty general case. And so I'm going to review the concept of self-inductance that we talked about way back in Circuits 1, although I don't think I called it self-inductance then. I probably just called it inductance. And then we're going to take some of the stuff that you guys should have learned in your Physics 202 class and kind of see where things go from there. Okay. So self and mutual inductance. So you guys should have learned in your Physics 202 class, and you will cover this in much greater detail next quarter in Electrical Engineering 313, that according to Ampere's circuital law, a wire carrying a current will generate a magnetic field and associated magnetic flux density. So if I have a simple section of wire, which I'm just drawing in black here, and this is part of a closed current carrying circuit, if my current I of t is flowing in this direction down the wire, so from left to right, what should my magnetic field look like? So I see some people throwing gang signs and all that kind of stuff. That's great. You guys at least loosely remember the right-hand rule. So based on the right-hand rule, if the current is flowing in the direction of our thumb, the magnetic field is going to wrap around in the direction of our fingers, right? So to me, that's going to look like this. So I'm going to draw this as some dots here. So we have these dots that I've drawn above the wire are trying to represent the head of an arrow that's directed out of the page, right? So if my current is flowing from left to right, I should see that the field lines are directed out of the page in regions of space above the wire. and they're going to be directed into the page in the region of space below the wire. Right? And these circles with X's inside of them are trying to represent us seeing the tail end of an arrow as it's sticking into the board. So that's how I'm trying to wrap my peon brain around this three-dimensional phenomenon that's happening. So hopefully that's clear to all of you. Our magnetic field, intensity B, as a function of time, is measured with the unit Tesla, capital T, where a Tesla is equal to a Weber per meter squared. And a Weber, for those of you that don't know or don't remember, is just a volt second. So a Tesla is simply a volt second per meter squared. That's the number one. Oh. What? I don't know, man. Feeling kindergarten? Not to be more of an ass than usual. All right. So what happens when we coil a current carrying wire? Right, so let's draw a picture. Okay. So I'm going to draw a cylindrical core here. I'm going to make this try to be as cylindrical as I can draw. And we're going to wrap a wire around this core. So if you had me for circuits 1, you've seen this picture or something very similar to it before. What is this thing?
It's a coil.
It's a coil or a solenoidal inductor, right? So let's say that this coil of wire has some specific number of turns. So N is just going to represent the number of turns. It's usually a relatively large number. So you might see some inductors where there's only like 3 or 5 turns or things like that. But usually it's 10 to 100. And if we're talking about the coil used to form like an electric guitar pickup, it might be several hundred turns on that inductor. Okay. So what's our magnetic field going to look like in this cylindrical coil system? So whenever we've got a coil of wire, if our fingers wrap around in the direction of the winding, our thumb tells us the direction of our magnetic field. It might seem a little bit weird because it's almost the exact opposite of what we had for a wire, where for just a straight section of wire, our thumb is the direction of current, our fingers are the direction of field. Now we've got our fingers are the direction of current and our thumb is the direction of field. But if we thought about just a single wire where our thumb wrapped around, we would see that the field lines are going to point up inside the ring and they're going to point down outside. And if we just stack a whole bunch of rings on top of each other, we're going to see, generally speaking, that the field is directed up inside the coil and down outside the coil, right? So I'm going to attempt to draw that. So along the axis of symmetry of our coil, we're just going to have a field line that is straight up and down. But as we get a little bit further away from our axis of symmetry, we're going to see that our field curls around to come back in on itself because there's no such thing as a magnetic monopole. We have dipoles, so it always has to form a closed loop. So it'll look something like this, where once again, these kind of blue-greenish lines represent our B field, magnetic flux density. So we are going to define magnetic flux as kind of the total amount of magnetic field lines that are passing through our coil. Okay? So our flux has a symbol of phi, and I'm going to choose to write it as phi b to remind us that it is magnetic flux. And mathematically, this is given by integral of our magnetic flux density field B dotted into a differential area unit A. So let's define our cross-sectional area for this coil. So what do you guys think the cross-sectional area of the coil is? Yeah, it's a cross-sectional area of a circle, right? So it's going to be something like this. And then our differential area element, dA, is just a small part of that cross-sectional area. So what is the direction of the vector area for this? And I might be wording that weirdly. So when we represent an area, we usually have a vector that represents that area that is orthogonal to that surface, right? Do you guys remember that kind of stuff? So orthogonal to the surface of this thing would be either up or down. I'm going to be lazy and just choose up. Okay? So if I have a B field that is direction up, and I have a vector area that is direction up, what does B dotted into dA look like? Just multiplication, right? When they're in the exact same direction, the cosine of the angle between those vectors is cosine of 0, which is just 1. So this magnetic flux, that's right, is just going to look like B multiplied by A. Sorry, this is drawing really weird all of a sudden. Like the sensitivity somehow got off. So I apologize if that looks sloppy. It starts drawing when my pen is like a millimeter away from the top of the thing. Don't know what's going on. I'll figure it out later. If you have any questions about any of this, because my handwriting is going to be crappier than usual, please let me know. Okay. So the unit of our magnetic flux is the Weber that we introduced earlier. Okay. So we have 1 Weber is equal to, gosh, this looks terrible, a volt second. Let me, yes. Yeah, like my pen is nowhere, it is not physically touching, and it is drawing stuff here. I'm about to save this and close this program and reopen it and hope that that fixes it. I don't know how I've managed to screw up my brand new Surface Pen. Okay, it's back to normal. Thank goodness. That was utterly terrible looking. Let me erase this and then draw it where it's remotely legible. So 1 Weber. Oh, now it's doing it again. Oh my gosh. Maybe. Nope, it's definitely doing it on the middle there. I will probably wind up making a scan of my notes and uploading them so they'll look a little bit better than this, but I'm going to continue on because I don't want to waste the entire time trying to troubleshoot my computer. Okay, so anyway, so we have this flux just B multiplied by the area, and we know that the instantaneous value of this magnetic flux density B depends on the amount of current that's flowing in our wire. So we're going to introduce something that you probably haven't heard of, may have been covered in your physics class, and that's going to be called a flux linkage. Okay, so flux linkage. Oh my gosh, this looks so bad. I don't know. Is it because this OneNote thing popped up? I hope not. Gosh, this looks so bad. Yeah, let me see something. That's really annoying. I'm sure it's some simple setting. Let me see if this one has any batteries. Oh, but now I have to remember how to use this one. Okay. This computer is like maybe 2 months oldish, and so other than when I was teaching Circuits 1 over the summer, it's the only time I've used it. All right, this one still looks bad, but not as bad as the other one, so I'll work with this for now. Okay, so flux linkage. So mathematically, our flux linkage has a symbol of lambda, and it is just N times our magnetic flux. So the flux linkage is really just telling us, all right, so we know we have some amount of flux that's passing through this coil, and it's going to happen N times because there are N turns in the coil. So we just add all that together to kind of get a total flux that's going on, okay? So our flux linkage is nothing more than a quantity also measured in Webers because it's just a number times a quantity measured in Webers, okay? Well, for a linear system, and so let me explain what I mean, and I don't want to get too far over you guys' head here. You will learn this in your later courses if you choose to go into the power series. So a linear system in the context of an inductor like this means that the core material that our coil is wrapped around has a constant value of what's called its permittivity. Permeability. That's the magnetic one. Okay? Now, the overwhelming majority of materials that are actually used inside an inductor do not have a constant value of permeability. So the materials that are usually used as the core of an inductor, at least for ones where we want to build something like a transformer, are ferromagnetic, and so their permeability depends on the external field that is applied to them. It's just not a material property. But if we have a system like this, where there is a large air gap, meaning that this isn't a closed core that forms a loop, that air gap tends to linearize the system. So any solenoidal inductor that we are ever going to see should behave like a linear magnetic system just because of the air gap at each side of the core material. It's just context here. It'll make a lot more sense when you get into the material science side of looking at these things, which you'll deal with as a senior. Just trying to give you some context here. Okay. So anyway, in a linear system, the flux linkage, lambda, and the current are related to each other by the self-inductance of our coil, okay? So we have the relationship lambda is equal to L times the current flowing in our coil. Now, according to Faraday's law of electromagnetic induction, a voltage will be induced across the terminals of our coil if there is a change in the magnetic flux linkage. So this is explained very slightly differently than when we talked about this in circuits 1, right? So in circuits 1, we talked about having some induced voltage. I'm going to just call it V of t, like so. And we said in circuits 1 that a voltage was induced due to a change in the magnetic flux. Now I'm saying a voltage is induced due to a change in flux linkage. Are those two different phenomena? I would argue no, because the flux linkage is dependent on the magnetic flux. The number of turns in the coil isn't going to change. So for the flux linkage to change, the magnetic flux has to change. So it's just the exact same thing that we talked about in circuits 1, explained a little bit different. Okay. So our induced voltage V of t is the derivative of our flux linkage with respect to time, which is in turn the derivative with respect to time of simply L times our current. And since L will be a constant, this is going to look like L times the derivative of our current with respect to time, which is just the relationship for the voltage drop across the inductor that we've been dealing with for literally over a year at this point. Okay. So we have reviewed self-inductance, provided a little bit more context. Everybody okay with what we've talked about thus far? Hopefully nothing's too wild or new, because other than the concept of flux linkage, this should all be reviewed. So here's where fun stuff happens. Okay. Did you guys talk about mutual inductance in your Physics 202 class? No, okay. I'm genuinely surprised about that. So this will be an interesting discussion.
We probably learned it, but we all forgot it.
That's fair too, for sure. Nope, that's absolutely fair. So we have this self-inductance thing here. So let me explain why it's called self-inductance, and then that'll kind of tip us off as to what's going on in mutual inductance. So we have a coil. We pass a current through said coil, and it generates a magnetic field that passes through the exact same coil that is providing the field. So it's self-inductance because the field that's generated by this coil passes through the same coil. Well, mutual inductance occurs whenever we have a coil like this and we place another coil near to it, so that some of the flux generated by coil 1 will pass through coil 2. And because of Faraday's law of induction and all this kind of stuff that we have down here, we will induce a voltage in that second coil as well, based on this relationship. Okay. Yes? It is how all transformers work, actually. Not only is it how all transformers work, how many of you guys have a cell phone that was made in the last 5 or 6 years? Is it capable of wireless charging? That's mutual induction. How many of you guys have ever listened to a radio? Antennas work on mutual induction. It is literally everywhere. Whether or not it's intentional is another bag of cats. So whenever we have a system that has intentional mutual inductance, we typically call that a transformer. But we'll get into all of that over the next several days. All right, so let's draw a little picture here. So let's say that I have the following system. So I've got a wire, and then I'm going to form a coil over here. Sorry, this isn't the pen. This is just my inability to draw. And then over here on the right-hand side, we are going to have another wire. Goodness gracious. And another coil. Mm-hmm. Like so. Okay. So I have two terribly drawn coils near each other. Okay. So I'm going to call this thing over here coil number 1. Goodness, this is also looking like it's going to hell. And coil number 1 is going to have N1 turns. And over on this side, I have coil number 2, and it's going to have N2 turns. N1 could be the same as N2. They could be close to each other. They could be vastly different. It doesn't really matter. The math behind it's all going to work out roughly the same. Okay. So I'm going to form a circuit on coil number 1. Okay. I'm going to do that by just putting a voltage source across coil 1. So if I were to apply some sort of sinusoidal excitation, like so, we would induce some voltage V1 of T across the terminals of coil number 1 because there is some current I1 of T flowing through that coil. And if our current changes, our flux changes. If our flux changes, our flux linkage changes. And if our flux linkage changes, we induce a voltage. Okay. So we are going to have some magnetic field lines. And I'm going to draw one. I'm using the wrong color here. Not that it particularly matters. It's going to circulate around like so. And I'm going to call this flux phi 1, 1. So that's the flux that's generated by coil 1 that's passing through coil 1. So that's what's causing our self-inductance. And then we're going to have some flux that's going to go the other way. And I'm going to call this flux phi 1, 2, where that means that it is the flux generated by coil 1 passing through coil 2. The closer I get those two coils together, the larger that flux phi 1, 2 should be, or the more flux is going to pass through that second coil, I guess would be a better way to put it. So I have a time varying flux that's passing through coil 2. So I should observe a time varying voltage drop across the terminals of coil number 2, even though there is literally no physical connection between coil 1 and coil 2. I'm able to create a voltage drop across coil 2. So let's talk about what that means in context, right? So think way back to the second day of circuits 1, at least if you had me. I define voltage in 2 ways, right? And in circuits 1, the way that the definition for voltage that we use the most was that voltage is just the difference in electric potential between 2 points in a circuit. That's still true, but the other definition, that voltage is the work done per unit charge in moving charge from point A to point B, is more applicable here, okay? So if there's work being done, then there's energy being transferred. So effectively, what we have is a system here where I'm able to wirelessly transfer energy from coil number 1 into coil number 2, even though they are not physically connected. And that is because they are magnetically coupled together. And that will be true for any 2 coils that are near each other when at least one of them is excited. Like I said earlier, this is literally how your wireless cell phone chargers and all of that kind of stuff works. The wireless cell phone chargers do it at a very specific frequency. I believe it's 13.56 gigahertz. It's been a couple of years since I had to play around with those. But if you look at them on a spectrum analyzer, it's just one distinct peak at one frequency because of the way those coils are designed. But anyway, so let's take a look at our induced voltage V2 here. And I want to be clear about this. I've got time, okay. I'm leaving coil 2 open circuited so that we don't have to worry about any current or anything in coil 2 just yet, right? So only talking about what the voltage is going to look like. So mathematically, our voltage V2 as a function of time is going to be simply the derivative of the flux linkage of coil 2 with respect to time. So what should the flux linkage of coil 2 be? So what's the definition of flux linkage that's slightly off of the screen but should be in you guys' notes? Number of turns. So we're talking about the flux linkage of coil 2 here. So should we be using N1 or N2? N2, right? And then what's the second term in our very simple flux linkage relationship? The flux, right? So the flux that's passing through coil 2 is the flux that I've labeled phi 1, 2 here. And so now we might have to do a little touch of algebra, okay? So there's nothing wrong with what we have here, but we're ultimately trying to relate our induced voltage back to a current so that we have a relationship that looks similar to the inductor relationship that we are expecting. So we know that phi12 depends on that current I1, right? So we could say if we look at this relationship right here, right? I want to rearrange this where we have phi b is equal to something in terms of I, right? So I think if I divide this guy right here by the number of turns, I'll get L over the number of turns times I of t. And we want everything here to be associated with what's going on in coil 1, because coil 1 is the guy that's producing this flux, right? So we should be able to say that phi12 is just L1 over N1 times I1 of t, using a little bit of algebra. Everybody okay with that? So that's going to look like the derivative with respect to time of N2 times L1, gosh, that looks bad, over N1 times I1 of t. I'm going to come down here below because I'm running out of room and play around with this, okay? So N1, N2, and L1 are all constants. So I can move them outside of my integral. So that's going to look like N2 divided by N1 times L1 times the derivative, right, of I1 as a function of time, or with respect to time, excuse me. And I'm going to call this combination of N2 over N1 multiplied by L1 the mutual inductance M21. And then we'll have dI1 by dt. So this is the voltage that's induced across coil 2, and it depends on multiple different parameters in our system, right? So it depends on the self-inductance of coil 1 and the ratio of the number of turns in coil 2 with respect to the number of turns in coil 1. So if we want a large mutual inductance, our second coil has to have many, many more turns than our first coil. And if we want to minimize mutual inductance, our second coil needs to have many, many less turns than coil 1. Okay. So this is the mutual inductance that coil 2 sees when coil 1 is the one that's energized. So what would happen to this system if we put our sinusoidal excitation source on the right-hand side, connected to coil 2, and left coil 1 open circuit? Effectively, it's the exact same system, except that coil 2 is the one that is excited. So let's write some things down here really quickly. If coil number 2 were excited while coil number 1 is open circuited, then the induced voltage across the terminals of coil 1 would be the derivative of the flux linkage in coil 1 with respect to time. And then I'm not going to go through all of these intermediate steps because they're almost exactly the same, but they're going to come out to look like N1 over N2 times L2 times the derivative of I2 with respect to time. And we're going to call that M12 di2 with respect to time. So this is the mutual inductance of coil 1 with respect to an energized coil 2. And notice that the ratio of the turns is flipped upside down. We've got L2 instead of L1. Now, an interesting thing is that electromagnetic fields, we're dealing with a magnetic field in this case, are conservative quantities, meaning that the law of conservation of energy has to be conserved in an electrical system like this. And the law of conservation of energy effectively tells us then that since energy must be conserved, the mutual inductance M21 has to be exactly equal to the mutual inductance M12. Because if they were any different, we would have created energy on either side of our system. Okay? So we can get rid of those pesky subscripts of 1, 2, and 2, 1 and trying to keep track of which coil is energized and which isn't by just saying that there is a mutual inductance M that couples two coils together in a closed system. So that's our mutual inductance term. Now, this will be the last thing that we'll do today. Let's talk about what might happen if we energized both sides. And it's really not important that I'm energizing both sides. It's more important that I'm closing the loop on both sides, to be clear here. Okay. So let's consider a system where we've got I drew that too long, but it doesn't matter. So there's one coil. Here's another coil. This is coil number 1. Once again, it has N1 turns. This is coil number 2. And once again, it has N2 turns. And I'm going to sinusoidally excite both sides. So I should observe a current I1 Goodness gracious, that looks like hot garbage. I1 of t like so. And let's just say that I'm going to have a current I2 of t, and I'm just going to choose a direction for it really quickly. I'm going to choose that it's flowing in towards the coil, like so. Well, I have two coils, and I have two currents. So I should definitely have an induced voltage across each of those coils just because of the self-inductance alone, right? So there's going to be some voltage here, V1, and there's going to be some voltage here, V2. Well, I'm going to have some flux as well. So I'm just going to have this flux over here. Let's call it phi 11. I'm going to have some flux over here. And let's call it phi 12. And then I'm also going to have a flux that couples both of these coils together. And let's just call that phi. So a couple of things here before we get into the math. I'm playing a little fast and loose with the directions of our coil windings. Let me explain what I mean by that with this terribly drawn picture, right? So I believe that I have drawn this coil over here. So our current is flowing in and our coil is wrapping around like this. So our flux should be coming out of the top, like so, in the indicated direction. Toby, what's up?
Why is the flux on the right not 2-2?
Oh, it should be. Sorry, I'll fix that. That's just a mental mistake on my part. Okay, thank you for that. If we look at what's going on in coil 2, my current is flowing in this way, and it's wound like so. So my flux should actually be direction down, which means this arrow should be turned around. I'm going to leave it drawn like this just for the sake of argument, because this is actually where one of the quote unquote difficult things about this comes into effect, particularly in schematic diagrams and all of that kind of stuff. So we're going to sort this out at the very beginning of class on Monday. But we have this system, and the way that I have drawn the flux lines are such that this flux here in the middle is a combination of these two fluxes, phi 11 and phi 22. So I'm saying that they are adding together. But that won't always be true. It depends on the direction the coil is wound, the direction the current is flowing, or the polarity of the induced voltage. So we're looking at a very, very general case where we're going to start and just say, for easiness' sake, let's make things add together. And then we'll worry about the details of when things are going to subtract and all that kind of stuff in a little bit. And I promise it's going to get easier. Okay. So the flux linkage for coil 1. So remind me of what our flux linkage is again, please. The number of turns times the flux. What was the other definition? Inductance times current, right? So we have a self-inductance for sure, but we also have a mutual inductance, right? So for coil 1, our flux linkage should be our self-inductance of coil 1. So that's just going to be L1 times I1 of T. Let me try to write this better. And then we're also going to have a second term that's going to be M times I2 of T. The reason why we have this term over here is because coil 2 is energized, and so some of the flux that's generated by coil 2 winds up passing through coil 1, and it's going to affect the induced voltage across coil 1. So it's going to be a combination of the self-inductance and the mutual inductance, which determines that voltage. And that's why I was getting into the stuff about whether or not we're going to have an additive combination of the fluxes or a subtractive combination of fluxes, because that's going to tell us whether the voltage is getting larger or getting smaller because of these effects. And again, we'll deal with that in a much more simplified way soon. We're going to have a flux linkage for coil 2 that's going to be pretty similar to this, right? So it should be L2 times, I2 plus M times I1. And if we try to determine our induced voltages, we'll see that V1 is just the derivative of flux linkage 1 with respect to time. So that's just going to be L1 times the derivative of our current I1 with respect to time plus M times the derivative of our current I2 with respect to time. And similarly, our induced voltage V2 will be the derivative of flux linkage 2 with respect to time, or L2 DI2 plus M DI1. All right. I think that is enough out of me for today, because we only have 4 minutes left of class, and also I'm really annoyed that I can't write for shit right now because my pens are being dumb. So anyway, I will upload, or somebody shoot me an email, please, to remind me to scan these notes so that I can upload them in a less shitty form for you all. And we'll pick up on what's called the dot convention on Monday, where a dot convention is just a way to effectively represent at a glance what the winding of a transformer is, so that we know whether things are add or subtract.
Homework posted for the class today?
There will be no homework for this class today. We won't start homework until we go over the dot convention, so that it's not such a pain in the butt to analyze these things.